Hi everyone, this video is on quadratic functions, how to recognize them, how to graph them, and how to apply them in real-life situations. So what you see right here are the notes. For example, there are two forms of quadratic functions. In general, if you see the highest exponent of 2 in both forms, you can recognize it as a quadratic function, either y equals ax squared plus bx plus c, or the vertex form, which is a little bit easier to see with the transformations. But here's something interesting that I want to show you in Desmos, which is a free graphing calculator. It's really easy to use, but there's something interesting you can do. You can graph functions, but you can actually put in the general form. Let's say y equals ax, and you can press a squared here for exponents plus bx plus c. That works for quadratic. This is for general exponents. And notice how you can actually add sliders. I can click on all of them. And what do the sliders do? You can actually play with them. For example, a equals 1. Well, what happens if we make a bigger? Well, if you notice, the graph kind of squeezes in, it becomes taller. So you can imagine the a times x squared, the constant, does affect the graph somehow. Now let's go the other direction. Then it becomes wider, and at some point it flips around, it looks like, and you can actually easily adjust the scale or the window, and you can see it. If you click on the parabola, you can see points of interest, like a vertex, the x-intercepts, and so on. So notice a negative, you actually flips the parabola or makes it go in the negative direction, versus positive does the other way around. So let's put it back on 1. Now the B is a little bit interesting. It can do, it looks like it's moving it around. It's a little bit harder to pinpoint, but you can actually correlate it with the vertexes. I'll show you a little bit later. But if you put B equals 0, well, it's then you're not going to have the x, you're only going to have x squared plus a constant. Then you'll see it's just a shift up and down. So notice the C can actually shift it up or down, and notice you can actually correlate it. What if you put it on 2? What does it mean about the original equation? It's ax squared plus 2. Or actually, since a is 1, it's just going to be x squared plus 2, and so on. So you can play around and see how it changes the graph. Now going back to the notes. So there's different things that we can learn about it. So there are different rules. Do not memorize them. See if you can actually figure them out, either by graphing it or playing around with it. So figure it out. Why do these rules apply? For example, why, if it's absolute value of a, if it's greater than 1, then the graph appears stretched or narrower or taller, and vice versa, compressed if it's less than 1. So why is it true? Same thing for the units, the h and the k. You can actually put on the in the Desmos, put in the vertex form and play around with h and k as the sliders, and you can find the same thing. So once you figure that out, then you can easily establish what are the shifts, what is the h and k, and so on. So here we have this example, which is just this quick one, -2 times x minus 1 squared plus 3. So a is -2, h is 1, and k is 3. So once you've played around with the rules, if a is -2, what does that mean? Well, it's reflected about x-axis because it's negative. It's stretched because a is greater than 1, the absolute value of it, regardless of the sign. And it's shifted 1 unit to the right. So again, the negative actually implies right. That's a little bit intuitively harder to grasp, but try to think about it, why that is. And 3 units up. So the up and down shift is more intuitive, as we've seen with the C. And you can graph it. This is the graph from Desmos, actually, that I pasted in the document, but which you can do. You can take it as a screenshot, or you can save it as a document if you create an account. Or you can graph it by hand. Of course, it's good experience. Here's the vertex 1, 3, and I don't think it's drawn to scale, but and then a is -2, so you can adjust it. And here's another parabola, y equals 1/3 x squared plus 1. So there is no horizontal shift, it looks like. We have a is equal to 1/3, h is equal to 0, and k equals to 1. So In this case, the graph is compressed and it's shifted 1 unit up. So again, try to figure out why that is instead of memorizing. It's a lot easier later on in the semester, but you can figure that out. Now let's focus on another method, and I'm actually going to make the window a little bit bigger. So the general form, it's a little bit more difficult because there is no transformations. You can actually bring it to the vertex form by completing the square, but that's for another time. But there's still an easy way, relatively easy way to graph if you note the A, B, and C. What are the constants? So A basically represents which way it opens. It's kind of similar to the shifts. The vertex has to be noted. It actually all goes back to quadratic formula. And again, there's various ways to memorize it. I'm sure on YouTube you can find the different songs about it. But the easy way basically to remember how the different pieces fit. So notice the negative b over 2a, that's actually the vertex, the x of the vertex. How do we find the y? Plug it back into the original equation. That's why we're using function notation here. And here's the vertex. So that already gives us 1 point automatically. The y-intercept is 0, c. So that's where the c is useful. Where is the y-intercept? And sometimes you can find a symmetric point to the y-intercept. So again, you get at least 1 or 2 points with the symmetry. X-intercepts you may or may not have, depending on the quadratic formula. Actually, it depends on this quantity, b squared minus 4ac under the radical. So if you note, if it's positive, what's happening here? We can actually draw this out. If it's positive, it's going to cross the x-axis in a couple of places. So like something like that, as you'll see, whether it's facing up or down. If it's 0, well, notice the square root of 0 is 0, so you're just going to be left with a vertex. So the vertex would be sitting right on the x-axis. And if it's negative, as we know, we're going to get complex numbers, but not real numbers. So it's not going to cross x-axis. So here's a quick example of it. Let's say it's facing down and it's going downwards and it never crosses x-axis. And again, you can find the symmetric point if you need to. So this, you can basically use this method for any parabola. Let's say if it's x squared minus 2x plus 4, we know that a, the coefficient of x squared is 1, b is the coefficient of x is negative 2, and c is 4. So the parabola opens up, the vertex, be careful with the negatives. There may be a lot of negatives here, but it's negative, and the b over 2a, so negative, two negatives here, divided by 2 times 1, and you simplify it. Sometimes you get fractions here, but it's 1. Plug it back into the quadratic equation above, and you'll get 3. So the vertex is 1, 3. Y-intercept is 0, c, which is 4. And you check the discriminant. It's negative, so there are no x-intercepts. Again, I'll leave it to you to check. And so what does the graph look like? So here we can plot 3 points. Here is the vertex, here is the y-intercept, here is the symmetric point, because every parabola has like axis of symmetry that goes right straight to the vertex. So basically, right on the other side, you'll have a symmetric point to graph. And that's all about graphing. It's very easy to do it by hand. You don't even need a calculator. Of course, you can use calculator to check with it, but it's nice to be able to do it by hand very quickly. And what are some applications? I'll discuss the 2 of them in business that are kind of relevant with maximum revenue or minimum cost. And of course, there's plenty of other applications, maximum height, if you throw a baseball, for example, and so on. So say a demand equation, which is really the price that depends on the quantity x, and it's 200 minus 4x is sold, and we need to find x, the quantity for which the revenue is maximum. So the revenue, you may have seen it in college algebra or previous courses, but basically the revenue, if you think about it, is the quantity times the price per unit. And that's sort of a relatively easy way to describe the revenue, but it works for this business. So we can multiply x times the demand equation, 200 minus 4x, we can distribute, and we can actually put it in the descending order. So we'll get negative 4x squared plus 200x. And now it becomes, if you notice, it's a quadratic function. So how do you find x that maximizes the revenue? Well, as you can see, it's probably going to be a vertex. So you can actually draw this out. So you'll have, let's say, x and the revenue that depends on x. And you're going to have something like that. It is possible to sell too many, where it's like a point of diminishing returns. But here would be the maximum, right at the vertex. So if you calculate it, negative b over 2a, and here negatives cancel out, as they should, because you should get a positive quantity. So it's 25 units. Plug it back into the revenue, and you'll find the maximum revenue is $2,500. Very useful, relatively easy. How do you find the price that gives you the maximum revenue? I call it the optimal price. You can actually plug it into the R equals P times X, as you see above here, and it's you divide by 25 on both sides, you'll get P equals $100. So a relatively easy example, but it definitely works. And minimizing cost is similar. Say if the cost is already provided for us, notice how it's a parabola that's facing up, so the cost is the opposite of revenue. And again, how do you find the x for which to minimize the cost? Now we can visualize it as something like this, and here is the cost is at the minimum. May not be quite zero, so that's how I'm drawing it. And x gives us 25 units again, if you calculate it. So these are just two couple of relatively simple vertex applications. And that's it for this section.